Hello there, Mr. Sutton here, bringing you the AB Calculus 6-2 Extra Practice number 3 solutions on separable differential equations. To solve this differential equation, it's crucial that I notice that I have an output variable, y, over here on the right side of the differential equation. That tells me that I need to use separation of variables. So let me start by doing that. On the left side, I'm going to have dy over y, or y to the negative 1, however you want to write that. And on the right side, I'm going to have 6x squared times dx. Now I have to take the antiderivative of each side. On the left side, that's ln absolute value of y. On the right side, using my reverse power rule, this bumps up to a 3. Dividing by that, I have 2x cubed plus c. Don't forget that plus c. Now to find the c value, I have to plug in my initial condition. So I've got 3 over e to the 54th going in for y on the left side. And on the right side, this is going to be 2 times negative 3 to the third power plus c. So let's see here. On the left side, this is going to be ln of 3, basically minus ln of e to the 54th. So that's just ln of 3 minus 54 when all is said and done. And then over here, this is negative 27 times 2, which is going to be negative 54. So if I had ln of 3 minus 54 on the left side, and I have negative 54 on the right side, those negative 54s are going to cancel when I add 54 to both sides. So I'm just left with c equals the ln of 3 when all is said and done. So a little bit of arithmetic I skipped to get to this step here. Now we have to plug this back in. But before we do that, we have to resolve this absolute value. Now they told us that the y value was positive 3 over e to the 54th. So if that's the y value, then in general, y is positive. The expression inside the absolute value here is positive. That's why I care. So that tells me that to get rid of the absolute value, I don't need to change anything. I just need to use a parentheses instead of an absolute value. So I can rewrite this as just ln of plain old y equals 2x cubed plus ln of 3. Now I have to isolate y. To do that, I'm just going to raise e to both sides. That gives me y equals e to all this stuff. And as one extra optional step, I could split up this expression into e to the 2x cubed times e to the ln of 3. And e to the ln of 3 is just 3. So this just becomes 3 e to the 2x cubed. On this problem, trying to solve this differential equation with the initial condition given here, since I have an output variable, y, in my differential equation, I have to use separation of variables on this one. So I'll start by dividing both sides by radical y to get it over with the dy. Now, if I have dy over the square root of y, I can really write that as y to the negative 1/2 power times dy. And then over on the right side, multiplying both sides by dx, I've got x dx. Taking the antiderivative of both sides, on the left side, this bumps up to an exponent of positive 1/2. Dividing by that, I have 2y times, or 2y to the 1/2 power. And then on the right side, this is going to be 1/2 x to the second power plus c. Plugging in my initial condition now to figure out the c value, this is going to be 2 times the square root of the y value they gave me, so 2 times the square root of 25 over 16. On the right side, I've got 1/2 times 1 squared plus c. So let's see here, square root of 25 over 16, that's really going to be 5 over 4, and 2 times that is going to be, let's see, 5 over, that's going to be 10 over 4, which is 5 halves. Now we have on the right side, this is just 1/2. 5 halves minus the 1/2 is going to give us 4 halves, which is just 2. So when we do all the arithmetic here and solve for c, we just end up with c equals 2, which isn't so bad. Plugging that back in here, I've got 2 times the square root of y equals 1/2 x squared plus 2. And now all I have to do is isolate y. So I can do that by first dividing everything by 2. So this would be 1/4 x squared plus 1. And then I have to raise both sides to the second power. So this is just going to be y equals all this stuff on the right here squared. On this problem, I'm trying to solve this differential equation with y of negative 1 equals 2 as my initial condition. Since I have an output variable, y, in the differential equation, I will use separation of variables for this. So first step, let's get y over to the left side by multiplying both sides by y. That's going to be y dy on the left. And we'll move dx over to the right side by multiplying by it as well. So that's equals 3x dx. Now to take the antiderivative of each side. On the left side, using the reverse power rule, this is going to be 1/2 y squared. And on the right side, this is going to be, let's see, this is also an x squared, and we're dividing by 2. So 3/2 x squared. Don't forget the plus c. To find the c, we have to plug in our initial condition. So I've got 1/2 times the y value 2 squared on the left side. On the right side, we have 3/2 times the x value negative 1 squared plus c. So back on the left side here, we have half of 4, which is 2. On the right side, this is just going to be a 1 here. So we have a 3/2. So to get c, we have to do 2 minus 3/2, which is 1/2 for my c value. Plugging that back in here, we have 1/2 y squared equals 3/2 x squared plus 1/2. Now we have to isolate y. I can start by multiplying everything by 2. So that's y squared equals just 3x squared plus 1. And now to get y by itself, I have to take the square root of both sides. Now, normally when you do this, you get a plus and minus root, but I can only have one of those for my final answer. So I have to look back at my initial condition here to see which of those branches I want, the positive or the negative. So I see here that my y value is 2. So if y is 2, then in general, we're looking for a positive y value when we take the square root. So I'm going to write y equals the positive square root of 3x squared plus 1. I did not pick the negative square root, I picked the positive. On this one, I'm trying to solve this differential equation. Now the key on this one is recognizing that we have y, an output variable, in our differential equation. So that means I'm going to have to use separation of variables to get y to be with the dy. So to do that, I'll divide both sides by y squared. So I have dy over y squared, or y to the negative 2 dy, however you want to write that. And then over on the right side, I'm going to get the dx over there by doing x times dx. Now to use the antiderivative for each side. On the left side, this bumps up to a negative 1. Dividing by that, I've got negative y to the negative 1. On the right side, this is going to be 1/2 x squared plus c. And now I have to plug in the initial condition here to find the c value. So on the left side, we have negative y value negative 2/7 to the negative 1. So a whole bunch of stuff is going to have to happen over there. We'll cross that bridge when we get there, though. On the right side, we have 1/2 times the x value 2 that's being squared, and we also still have the plus c. So let's see here. On the left side, we're taking the reciprocal. The exponent happens first. So this is negative 7 over 2. Then that gets negated. So this is going to be positive 7 over 2. On the right side, we just have 2. So to get c, we have to do 7/2 minus 2. That's going to be 7/2 minus 4/2, which is going to be 3/2 for the c value. Now we have to plug that back in here for c. So we have negative y to the negative 1 equals 1/2 x squared plus 3/2. And now we just have to isolate y. Now there are a few ways that you can go about this. I find that in this kind of situation, I know I'm going to be taking a reciprocal at some point because I have this y to the negative 1. So I prefer to get everything on the right side together into one big fraction. And that's not so bad because I've already got a common denominator of 2 here. So I can rewrite the right side as x squared plus 3 all over 2. And at this point, before I do any reciprocal stuff, I want to get rid of this negative out in front. So I'm going to negate both sides, which just gives me a negative version of this fraction over on the right side. And then finally, I'm going to go ahead and take the reciprocal of both sides. So I have y equals negative 2 over x squared plus 3 for my final, most simplified, nice-looking answer. On this one, to find this differential equation's solution, I have to notice that there's an output variable in the equation, so that means I need separation of variables. I'll start by dividing both sides by y squared, which means I have dy over y squared on the left side, which is to say y to the negative 2 times dy. And I also have to get the dx over on the right side. This is the whole separation of variables thing. The x's go with x's, the y's go with y's. So on the right side then I have 3x dx. Taking the antiderivative for each side, on the left side this bumps up to a negative 1. Dividing by that, I've got negative y to the negative 1. On the right side, this bumps up to a 2, so that's going to be 3 halves x squared plus c. To find that plus c, we have to plug in our initial condition. So on the left side, this is going to be negative, and inside of parentheses, negative 1/3 to the negative 1. Whole lot of negatives over there. And on the right side, we have the x value 1 getting plugged in for x. No other change, though. So back to the left side here. We have negative 1/3 to the negative 1. That's going to be negative 3 over 1, or just negative 3. But we already have a negative out in front of all that, so when the dust settles, we have 3 on the left side. On the right side, this is just 3 halves times 1, so 3 halves. So we essentially have 3 minus this 3 halves. That's what we need to do to find the c value. Well, 3 is really 6 halves, so 6 halves minus 3 halves is just another 3 halves. That's going to be our c value, 3 halves. Plugging that back in for c right here, we come up with this version of the differential equation, which we're almost there. Actually, not the differential equation. This is the solution, this version of our particular solution. But in order to really be done with this, we have to isolate y. So I'm going to do a couple things here. One thing I'm going to do is merge this fraction together. So this is going to be 3x squared plus 3 all over 2. Then I'm going to get rid of this negative by dividing both sides by negative 1. Just gives me a negative version of that fraction I just wrote. And then finally, now that I've got one big fraction here, I can take the reciprocal of both sides to get y equals negative 2 over 3x squared plus 3. On this problem, I'm trying to find the solution to this differential equation, trying to find out what y equals. So one thing I notice here is that I have my output variable, y, in the differential equation. So that tells me that I need to use separation of variables to solve this. So I'll divide both sides by y to get it over with the dy. That allows me to write y to the negative 1 dy, or dy over y, however you want to write that. And now I have to also multiply both sides by dx to get it over to the right side. So that's going to be 1 plus ln of x quantity times dx. At this point, it's time to take the antiderivative of each side. On the left side, I've just got ln absolute value of y. On the right side, going from left to right, we've got x. That's what the 1 turns into. And we have the antiderivative of ln of x. Well, what is the antiderivative of ln of x? So at this point, there's a little bit of a divergence in our solution here. If you are doing this for BC calculus, then you would need to earn this using integration by parts, which I will show you now. If you were doing this for AB calculus, then I just gave you the antiderivative of ln of x, and you can pretty much just use it for free without doing all this stuff. So for AB calculus, feel free to follow along or just skip ahead to the antiderivative I already gave you for ln of x. BC calculus, follow closely because you need to do this with integration by parts. So here's our integration by parts formula again. We have the antiderivative of u dv equals uv minus integral of v du. As always with integration by parts, we have to pick out the u and the dv values in the beginning. Now you might be thinking, well, how would I even know this was integration by parts? Usually that's when you have two things being multiplied together and nothing else is working. What two things are being multiplied together up here? We have ln of x. We also have 1. 1 is the other thing, or you could think of it as maybe 1 dx, however you want to think about this. So when I'm picking my u value, I want to pick something that's easy to take the derivative of. That doesn't really help me pick ln of x versus 1. But when I'm picking my dv value, I want to pick something that I can take the antiderivative of. Now, between the two things, 1 and ln of x, I know how to take the antiderivative of 1. I do not know how to take the antiderivative of ln of x. Otherwise, I would have done it already, because that's what the whole question is. So I'm going to let the u value be the thing that I don't know how to take the antiderivative of. My u value is going to be ln of x here. That means my dv value I'm going to write as 1. 1 dx. All right, so let's go ahead and take the derivative of ln of x. So du is going to be 1 over x dx. And for v, the antiderivative of 1 dx, that's just going to be x. So for uv, multiplying these together, I have x times the ln of x. And for minus the integral of v du, well, the x and the 1 over x are going to cancel, leaving me with just a 1 dx inside that integral. So this ultimately becomes x ln of x minus x. And there's a plus c in there, but we're just going to throw the plus c in over there. So yeah, for BC calculus, you had to earn this with integration by parts. AB calculus, I just gave this to you, and you weren't really expected to do all of this because this is a BC calculus topic, integration by parts. But I wanted you to still have the joy of doing this problem in general. So anyway, coming back here, we have a plus ln of x minus x plus c. Cannot forget the plus c after all that work. And I'm going to simplify a little bit because we have a plus x and a minus x. So let's just simplify a little bit so that there's less places to plug things in. But now at this point we do have to plug in to find the c value. So I have a y value of 1. That's going in here with the absolute value. And I have an x value of 1. So we have 1 times ln of 1 plus c. So a whole bunch of good stuff's going to happen here. Ln of 1 is just 0. Ln of 1 is still 0. Times 1 is still 0. So c equals 0 when all is said and done. So going back here, we can write ln. Well, we actually have to figure out this absolute value. Before we even plug in c, let's resolve this absolute value. Now, they told us that y is 1. Well, if y is 1, then the stuff inside this absolute value, which just happens to be the single expression y, that's going to be positive stuff. So that means to get rid of the absolute value, I just have to replace it with the parentheses. I don't have to negate the input or anything like that. So I can write this now as ln of just plain old y equals x times the ln of x plus 0, and I'm not going to bother writing plus 0. To actually solve this, though, I have to isolate y, which means I have to raise e to both sides of this equation. So when all is said and done, then I can write y equals e to the x ln of x power, which ends up giving me, let's see here, answer choice E. On this free response problem, we have a boiled potato taken from a pot at time 0 and left to cool in a kitchen. Internal temperature is about 91 degrees Celsius at time 0, and the internal temperature is greater than 27 for all times, positive times here. Internal temperature can be modeled by the h function, whose differential equation is this dH over dt business here. And h of t is measured in degrees Celsius, and h of 0 is 91. So they're not giving us the h function, but they're telling us that at time 0 it gives you back a value of 91. So first task on this one, we want an equation for the line tangent to the graph of h, which again they're not showing us explicitly, at time 0, and then use it to approximate internal temperature at time 3. All right, so tangent line equation in general, using our tangent line formula, we need h of some starting value. So like in general, h of a plus h prime of a times x minus a. Now in this case, the launching off point is 0. That's the a value for this. So our tangent line is going to be of the form L of x equals h of 0 plus h prime of 0 times x minus 0. H of 0 they already gave us. That's 91. H prime of 0, we're going to have to use this differential equation to find. So this is a little bit tricky here because this differential equation doesn't take 0 as an input because 0 is a t value. Instead, this differential equation takes h as an input. So if you want to plug 0 into this differential equation, you actually have to plug in the h value that goes with 0, which is to say 91. So this is going to be negative 1/4 91 minus 27. And 91 minus 27, let's see here, that's going to be 64. Negative a fourth of that is going to be negative 16. So that is our h prime of 0. Okay? So now going back to our L of x function that we've written for the tangent line to h, we have L of x equals, now we said h of 0 was 91, plus, well actually minus this 16 here that we just came up with. And then we have x minus 0, because we had an input value of time 0 for all this. And now they want us to approximate the temperature at time 3. So I'm going to say h of 3, and now I'm going to be very careful here. I'm going to write that this is approximately equal to 91 minus 16 times x minus 3, or x minus 0. So that's going to be 3 minus 0. All right, so we've got, let's see here, this is negative 16 times 3. I don't actually have to simplify this as long as I put units on, but this is 91 minus 48, which comes out to 43. And let's see here, that's going to be in degrees Celsius for the temperature. For this part of the problem, they want us to use the second derivative of h to figure out whether our answer in part A was an under or overestimate at time t. So to take the second derivative, we have to take our first derivative here, and we're actually going to have to implicitly differentiate on this one because we have an output variable h inside the function. So that means we have to multiply whatever we get by taking the derivative of all this stuff, we have to multiply it by the derivative of h, the tail of the chain rule there. So this is going to be negative 1/4, that's the outer part of this, times the derivative of the something here, which is going to be dh over dt. Now dh over dt, the thing that we just took the derivative of, we're actually going to substitute that whole thing in for this dh over dt that we just happened to get by using the chain rule. So I can rewrite this as negative 1/4 times all of this stuff right here. And if I simplify that a little bit, which is helpful here, we have positive 1 over 16 times h minus 27. Now at some point I need to figure out if the second derivative is negative or positive, because the whole under versus over thing on tangent lines is based on concavity, and that is based on the second derivative being positive or negative. Since they told me that my temperature, h, is greater than 27 for all times greater than 0, since h is greater than 27, that means that this stuff here, since I'm plugging in numbers bigger than 27, this stuff has to come out positive. The second derivative of h must be positive for all times greater than 0. Now what this tells us is that we are concave up if the second derivative is positive. We're concave up. Specifically, and I'm going to write this down, we're concave up on the interval from 0 to 3. Now, the reason I'm really making a point of specifying 0 and 3, 0 was kind of your point of tangency, your launching off point for your tangent line approximation that we're trying to figure out if we under or overestimated. 3 was your plug-in value. So we need to show that we're concave up on the interval from the point of tangency to the plug-in value. Now that we've done that, if we are concave up, it means we're consistently going to be under the curve, whichever way it is. So we are underestimating then by using our approximation. For this part of the problem, for time less than 10, we have an alternate model for the internal temperature of our potato. The differential equation for that model, which was going by the function g, that differential equation is given right here. It's this crazy negative g minus 27 to the 2/3 expression. Now, we're also given that g of 0 is 91. Our task on this is to find an expression for g of t. Again, they didn't give us that. They gave us its derivative up here. And then, based on the model, find the internal temperature at time 3. So one thing to realize is this is a completely separate problem from everything you thought you knew about this free response question. Like all the stuff that came before, I didn't bother rewriting it because this might as well just be a completely different problem. So here's our starting point. We need to take the antiderivative, but first, because I have an output variable, g, in my differential equation, I need to separate my variables. Otherwise, nothing is going to work out here. So to separate my variables, this is a little bit tricky because it's tough to isolate this g expression. So what I'm going to do is I'm basically going to divide both sides by everything over here, this whole negative g to the 2/3 expression. I'm going to put all of that under dg, or I'm going to make this a negative exponent when I move this to the other side. like so. So negative all of this stuff to the negative 2/3 power dg. Basically divided everything by this whole expression. So that's part one of separating the variables, is getting all the stuff that has this g sort of hidden away in it to be with the dg. But now what happens to this dt? I have to multiply it over to the other side. And what's on the other side? Well, if I've divided by all this negative g stuff here, I only have 1 left over on the other side. So this is a 1 dt, or just simply dt you could call it. At this point now, I can and have to take the antiderivative of both sides. So for the left side, we're going to use the reverse power rule. This bumps up to a power of positive 1/3, just adding 1 to negative 2/3, and then dividing by 1/3, really multiplying by 3. So this is negative 3 g minus 27 quantity to the 1/3 power. And then over on the right side, this is going to be, using the reverse line rule, this is just going to be t, and don't forget the plus c as well. Now we have to figure out the c value in order to have any hope of getting a g function. To get c, we have to plug in our initial condition. They said at time 0, our g function has a value of 91. So this g right here, I'm going to plug 91 in for that from my initial condition. And then this t I'm going to replace with 0. And at this point, we're just solving for c. So let's see, 91 minus 27, that's going to be 64. 1/3 power is really the cube root. The cube root of 64 is just 4. So we have negative 3 times 4, which is negative 12. And there's nothing left on the right side except for c. So we conclude then that c has a value of negative 12. Now I'm going to go ahead and plug that back into this version of my equation here. So I have negative 3 g minus 27 to the 1/3 equals t minus 12. But I'm not quite done doing what they asked me to do, which is to find an expression for g of t. In order to do that, I have to isolate the g in here. So I'm going to divide both sides by negative 3. That's negative 1/3 plus 4 on the other side, or negative 1/3 t, I should say. And then we have to raise both sides to the 1/3 power, or to the positive 3 power, to get rid of this 1/3 here. So I have all this stuff cubed, and that's going to leave me with g minus 27. I'm going to add the 27 over there to also get rid of that. So here's my g of t function. Now, in order to figure out the temperature at time 3, I'm doing g of 3, which is all of this stuff with 3 plugged in. And let's see here, negative 1/3 times 3, that's going to be negative 1, plus 4 is 3. 3 cubed is 27, and 27 plus the 27 out here comes out to 54, and that is going to be degrees Celsius.